There is a particular kind of silence that belongs only to the deepest reaches of space, not the silence of emptiness, but the silence of distance, of light that has been traveling for so long that the place it came from no longer exists in the form it once held. It is the silence of a message sent across an unimaginable gulf, arriving now in our instruments, carrying news of something that happened before our sun was born, before our planet had even the faintest chemical precursor to what would one day become life. This is the silence that the James Webb Space Telescope listens to with extraordinary patience, its golden mirrors cooled to temperatures barely above absolute zero, its detectors tuned to wavelengths of infrared light that the human eye could never perceive, its gaze directed at patches of sky so small and so apparently empty that a person standing beneath a clear night sky would see nothing there, nothing at all. With any instrument short of the most powerful observatories our civilization has ever constructed. And yet, within those seemingly vacant patches of cosmic darkness, the telescope finds things that should not be there, or rather, things that should not be there yet. Galaxies that are too massive, too mature, too chemically complex for the age of the universe in which they appear to exist. Galaxies that were born too soon, that grew too fast, that challenge in quiet but profound ways the models and frameworks that generations of astronomers have built with great care and great confidence over decades of observation and theoretical refinement. Bend one such galaxy, or more precisely one category of such galaxies, now increasingly well documented in the early observational campaigns of the James Webb Space Telescope, sits at the heart of a story that is simultaneously very old and very new. Old because the light we are receiving left its source more than 13 billion years ago, when the universe was a fraction of its current age, when the cosmos was a place so different from what it is today that calling it by the same name feels almost like a category error. New because the instruments capable of seeing that light with the clarity and sensitivity required to understand what it is telling us have only recently come online, have only recently begun their methodical survey of a universe that has been waiting to be properly read for as long as there have been minds capable of asking questions about it. The story of these early, massive galaxies, these objects that astronomers sometimes describe informally as galaxies that appear to have been born too soon, is a story about what happens when the universe surprises us, fate outruns theory, when the data refuses to fit neatly into the boxes that our best models have prepared for it. To understand why these galaxies are surprising, it is necessary to first understand, at least in broad outline, what the prevailing theory of galaxy formation predicts and why those predictions seemed, for a long time, to be in such good agreement with what we could observe. The framework within which modern cosmologists work is called the lambda cold dark matter model, often abbreviated as THIMCDM, and it represents one of the most successful theoretical structures in the history of science, a model that correctly accounts for an enormous range of observations, from the distribution of galaxies on the largest scales to the subtle temperature fluctuations in the cosmic microwave background radiation, the faint afterglow of the Big Bang itself. Within this framework, the universe began approximately 600 billion years ago in an event of extraordinary density and temperature, and it rapidly cooled and began to form structure through the action of gravity operating on tiny initial fluctuations in the density of matter. Dark matter, which interacts with ordinary matter only through gravity and does not emit or absorb light, played a crucial role in this process, clumping together first into what are called dark matter halos, gravitational wells into which ordinary or baryonic matter subsequently fell, condensed, cooled further, and eventually formed stars. The critical prediction of this model, the one that makes the existence of very massive, very mature galaxies in the very early universe, so challenging to accommodate, is that structure formation is hierarchical. Small things form first, and large things form later, assembled gradually through the merging and accretion of smaller components. In this picture, the first stars in the universe, the so-called population 3 stars, enormous and brilliant but composed almost entirely of hydrogen and helium, with none of the heavier elements that subsequent generations of stars would produce, formed within a few 100 million years of the Big Bang. These stars burned fast and died violently, seeding the surrounding gas with the first heavy elements through supernova explosions. The first small galaxies, tiny by the standards of what we see in the present-day universe, began to take shape within the first billion years, and the large, majestic galaxies that we see in the nearby universe, the Milky Way, the Andromeda Galaxy, the great elliptical galaxies that sit at the centers of massive galaxy clusters, were supposed to have assembled gradually over billions of years through the slow accretion of gas and the merging of smaller progenitors. The universe, in this telling, is a patient architect building its grandest structures only after long preparation and incremental accumulation. This is not merely a theoretical preference. It is a prediction grounded in the physics of gravitational collapse, in the statistics of density fluctuations in the early universe, in the behavior of dark matter as inferred from a vast array of independent observations. And for many years, observations appeared to support it. As telescope technology improved and astronomers were able to peer deeper into the universe, and therefore further back in time, since light takes time to travel, and the most distant objects we see are the youngest, the galaxies they found in the early universe were, on the whole, smaller, less massive, less chemically enriched than those of the present day. The universe appeared, in this light, to be maturing along the expected trajectory, its galaxies growing from humble beginnings into the grand structures of the modern cosmos. It's man's but the James Webb Space Telescope, launched on the 25th of December, 1804. After decades of development, cost overruns, technical challenges, and an anticipation that built within the astronomical community to something approaching collective breathlessness, has begun to complicate this picture in ways that are simultaneously exciting and deeply thought-provoking. The telescope's primary advantage over its predecessors, including the Hubble Space Telescope, which has been one of the most productive scientific instruments in human history, lies in its sensitivity to infrared light. This matters enormously for the study of the early universe because of a phenomenon called cosmological redshift. As the universe expands, the wavelengths of light traveling through it are stretched, shifted toward the red end of the spectrum and beyond, into the infrared. Light emitted by galaxies in the very early universe, when it finally arrives at our detectors after a journey of 13 billion or more light-years, has been redshifted so dramatically that it arrives not as visible light but as infrared radiation. Hubble, designed primarily for visible and near-ultraviolet observations, could see some of this infrared light, but not with the sensitivity or resolution required to study the earliest galaxies in detail. Webb, with its low-dent WoV-meter primary mirror composed of 18 hexagonal gold-coated beryllium segments, its suite of infrared cameras and spectrographs, its suite infractions to the Pretschens Comsity Spritz graphs, suite set is infraredens and spectroids, infrared comers and spectrographs, and its sun shield the size of a tennis court that keeps its instruments at temperatures close to minus 600 degrees Celsius, can see what Hubble could not, and what it is seeing is changing the conversation. Among the earliest and most striking results from the Webb telescope were observations of galaxies at redshifts greater than 10, corresponding to a time when the universe was less than C/4 million years old, less than 3.5% of its current age. That appeared to be far more massive, and far more luminous than the standard model predicted should be possible at such an early epoch. A study published in late Arsenling RCR by Labbe and colleagues, using early Webb imaging data from the Sears survey, identified a population of candidate galaxies at high redshifts with stellar masses, potentially reaching several hundred billion solar masses comparable to the largest galaxies in the present-day universe, existing at a time when, according to the Theta-CDM model, there simply had not been enough time for that much stellar mass to assemble. The paper, published in the journal Nature, caused a significant stir within the astronomical community, prompting both excitement about what these objects might tell us and careful scrutiny of whether the photometric redshift estimates and mass calculations were reliable, given that photometric measurements, which infer redshift from the colors of galaxies, rather than from the detailed analysis of spectral lines, carry significant uncertainties. But as spectroscopic follow-up observations accumulated, confirming the redshifts of some of these remarkable objects with much greater precision, the fundamental puzzle did not go away. It deepened. Means to appreciate the full weight of what the telescope is revealing. It helps to sit for a moment with the numbers, not to be dazzled by their magnitude, which can sometimes have the paradoxical effect of numbing rather than illuminating, but to let them settle into something meaningful. When astronomers say that a galaxy exists at a redshift of 12, they mean that the light we are receiving from it was emitted when the universe was approximately 7 million years old. The universe is currently about 600 billion years old. This means that the light from such a galaxy has been traveling for roughly 600 billion years before entering the Webb telescope's mirrors. In that time, the universe has expanded so dramatically that the galaxy itself, if it still exists in any recognizable form, now resides at a co-moving distance of perhaps 100 billion light-years from us. A distance so large that it exceeds the age of the universe in light-years, a fact that seems paradoxical until one remembers that space itself has been expanding during the journey of that ancient light. When we observe a galaxy at redshift 12, we are not looking at something 600 billion light-years away. In any simple sense, we are looking at light that left a place which has since moved, carried by the expansion of space itself, to a location far more remote than the travel time of the light alone would suggest. We are, in the most literal sense available to us, reading a message from a time before almost anything we would recognize in the universe had taken shape, a time when the universe was still, in cosmological terms, an infant. Its structures barely sketched in the gravitational medium of dark matter and primordial gas, its story only just beginning to acquire the complexity that would eventually lead, across billions of years of slow and patient evolution, to the formation of stars like our Sun, planets like our Earth, and minds capable of building telescopes to look back at all of it. And yet within that infancy, within those first few 100 million years that the standard model describes as a time of small, humble beginnings, something appears to have gone very differently than expected. Something large was already there, already assembled, already glowing with the light of billions or hundreds of billions of stars, and the question of how that could have happened, how the universe could have built something so massive so quickly, is one of the most quietly urgent questions in contemporary astrophysics. It is worth pausing here to consider what it actually means for a galaxy to be massive in the context of the early universe, because the word itself, massive, carries a weight that can be misunderstood if approached too casually. When astronomers speak of a galaxy's stellar mass, They are referring to the total mass of all the stars within it, expressed in units of solar masses, where one solar mass is approximately 2 times 10 to the power of 30 kilograms, or roughly the mass of our own Sun. A galaxy like the Milky Way contains somewhere between and cubic billion solar masses of stars. A number so large that even repeating it slowly does little to make it intuitively graspable. And yet, in the present-day universe, the Milky Way is considered a relatively modest galaxy. There are elliptical galaxies at the centers of massive galaxy clusters, objects like M/T, whose supermassive black hole was famously imaged by the Event Horizon Telescope in Arsienling Isarjol, that contains several trillion solar masses of stars, and whose formation histories span most of the age of the universe. These objects took a long time to become what they are. They assembled their stellar mass through billions of years of star formation and merging events, their growth regulated by a complex interplay of gas accretion, stellar feedback, and the activity of their central supermassive black holes. The idea that a galaxy containing even a fraction of this stellar mass could exist, when the universe was only a few 100 million years old, before the slow, hierarchical process of structure formation had time to operate, strikes at Yuchi something fundamental in our understanding of how the cosmos builds itself. The challenge is not merely qualitative, it is quantitative, and the numbers are instructive. In the SEAM-CDM framework, the rate at which dark matter halos grow, and the rate at which gas within those halos can cool and form stars, is constrained by well-understood physical processes. The universe's expansion rate, the initial amplitude of density fluctuations, the properties of dark matter, all of these set limits on how much stellar mass can plausibly accumulate within a given volume by a given time. Models that incorporate all of these constraints, and they are among the most sophisticated computational simulations ever constructed, requiring supercomputers running for months to produce a single realization of cosmic structure. Formation predict a certain number of very massive galaxies at high redshifts, and that predicted number is substantially smaller than what the Webb telescope appears to be finding. Some early analyses suggested that the observed number density of massive galaxy candidates at redshifts above 8 or 9 exceeded the model predictions by factors of 10, 50, or in some cases even more, though these early estimates have been refined as spectroscopic confirmations. Have accumulated, and as the community has worked carefully through the uncertainties in photometric mass estimates, can be substantial. Even with conservative corrections, however, a tension remains, a real, documented, peer-reviewed tension between what the best available theory predicts and what the most sensitive telescope ever built is observing. This tension has generated a rich and ongoing scientific conversation, one that unfolds across conference presentations, preprint servers, and the pages of journals with the particular quality of excitement that characterizes a field genuinely grappling with something new. Some researchers have argued that the tension can be resolved within the existing framework, that the photometric redshift estimates for at least some of these candidate massive early galaxies are incorrect, that dust attenuation or unusual stellar populations are causing their luminosities, and therefore their inferred masses, to be overestimated. Others have suggested that the star formation efficiency in the early universe may have been significantly higher than current models assume, that in the dense, turbulent, metal-poor environments of early galaxies, a larger fraction of available gas was converted into stars per unit time than in the more regulated environments of later epochs. Still others have proposed that the initial mass function of stars in the early universe, the distribution of stellar masses at birth, which determines how much light a given population of stars produces per unit of total stellar mass, may have been skewed toward more massive stars, meaning that early galaxies would have been more luminous than their total stellar mass alone would suggest by present-day standards. And a smaller but intellectually serious group of researchers has begun to ask whether the tension is pointing towards something more fundamental, whether it is a signal that the THMCDM model itself, for all its successes, requires modification at some level, whether in the properties assumed for dark matter, in the physics of the very early universe, or in aspects of cosmology that current models do not yet adequately capture. Each of these proposed resolutions is scientifically legitimate, and each carries its own set of testable predictions. This is, in fact, one of the most reassuring aspects of the situation, that the anomaly the Webb telescope has revealed is not a vague or ambiguous one, but a specific quantifiable discrepancy that can, in principle, be addressed through further observation and theoretical development. The telescope itself is ideally positioned to do much of the necessary work. Its spectrographic instruments, particularly the near-infrared spectrograph, known as NIR-SPEC, and the mid-infrared instrument, known as MIRI, can measure the spectra of individual galaxies with enough precision to determine not only their redshifts with high accuracy, but also their chemical compositions, their star formation rates, the ages of their stellar populations, and the properties of any active galactic nuclei, accreting supermassive black holes that may be contributing to their luminosity. Each of these measurements adds a layer of information to the picture, and together they build a portrait of these early galaxies that is far richer and more constraining than any photometric survey alone could provide. One of the most striking spectroscopic results to emerge from the Webb telescope's early science programs concerns not just the existence of massive galaxies in the early universe, but the degree to which some of them appear to be already quiescent, already finished with their star formation at redshifts that place them within the first billion years of cosmic history. In the present-day universe, the most massive galaxies are predominantly elliptical galaxies, red in color, their stellar populations old and relatively uniform, their star formation rates negligible. Astronomers have long understood that these galaxies must have formed the bulk of their stars early and quickly, a process sometimes called downsizing, which refers to the observation that more massive galaxies appear to have formed their stars earlier and over shorter timescales than less massive ones, in apparent tension with the simple hierarchical picture. But finding galaxies that are already massive and already quiescent at redshifts of 3, 4, or 5, corresponding to epochs when the universe was only 2.3 billion years old, was already surprising in the era before Webb. Finding hints of quiescent or rapidly quenching galaxies at redshifts of 7, 8, or beyond within the first billion years is remarkable in a way that demands explanation. The quenching of star formation in a galaxy, the process by which a once productive system of star formation is brought to a halt, sometimes gradually and sometimes quite suddenly, is itself a phenomenon of considerable complexity and active research interest. In the present-day universe, the leading mechanisms proposed for quenching include feedback from active galactic nuclei, in which the energy released by an accreting supermassive black hole heats and expels the surrounding gas, removing the fuel for further star formation, feedback from supernovae and stellar winds, which can drive powerful outflows of gas from less massive galaxies, and environmental effects, such as ram pressure stripping, in which a galaxy moving through the hot gas of a galaxy cluster has its own gas reservoir swept away. In the early universe, where the environments are denser, the gas interactions higher, and the dynamical timescales shorter, the relative importance of these mechanisms may be quite different, and the fact that Some early galaxies appear to have quenched their star formation within the first billion years, implies either that the relevant feedback processes were operating with extraordinary efficiency, or that some additional mechanism, perhaps not yet fully identified, was at work. Mainstreamians, the black holes that sit at the centers of galaxies, supermassive black holes, with masses ranging from millions to billions of solar masses, are increasingly recognized as essential actors in the story of galaxy formation and evolution, and their role in the early universe is one of the most actively studied and most puzzling aspects of the current observational frontier. The Webb telescope has already begun to reveal active galactic nuclei, quasars, and their less luminous cousins at redshifts that push the boundaries of what was previously accessible, and some of these early black holes are themselves surprisingly massive, raising questions about how they grew so large so quickly. The connection between the growth of supermassive black holes and the formation and evolution of their host galaxies is known to be intimate. The masses of supermassive black holes correlate tightly with the properties of the stellar bulges of their host galaxies in the present-day universe, a relationship that implies a deep company evolutionary history, but the details of how this company evolution unfolds in the extreme conditions of the early universe remain an open and fascinating question, one that the Webb telescope is uniquely positioned to illuminate. Indeed, as we deepen our engagement with the data that the telescope is producing, it becomes clear that the story of these early, massive galaxies is not a single story but a collection of related stories, each adding a different facet to a picture that is still being assembled, with great care and with an appropriate degree of scientific humility. The scope does not shout its finding. It whispers them in photons that have been traveling since before our solar system existed, each one carrying a tiny fragment of information about a cosmos that was already doing extraordinary things when the matter that would one day become you and me and everything we know was still diffuse gas drifting in the dark. And yet somehow, in the physics of that early darkness, something was already organizing itself with a speed and efficiency that our most carefully constructed models did not fully anticipate. There is something quietly humbling about this realization, something that invites a kind of reflective pause in the midst of the Tori Sitsathires. All the technical complexity and numerical precision that characterizes modern astrophysics. Science, at its best, is not merely a process of confirming what we already believe. It is a process of genuine encounter with a reality that is under no obligation to conform to our expectations, and the early universe, as revealed by the James Webb Space Telescope, appears to be exercising that independence with a certain unhurried indifference to the neat categories we have prepared for it. To understand more fully what the telescope is actually doing when it observes these distant galaxies, not just in abstract terms, but in the concrete, almost intimate terms of photons and detectors and the physics of measurement, it is worth tracing. The journey of the light itself from its source to the mirror of the telescope. A galaxy in the early universe, at a redshift of, say, 10 or 12, is producing light through the combined output of billions of stars undergoing nuclear fusion in their cores, converting hydrogen into helium and releasing energy in the form of electromagnetic radiation across a broad range of wavelengths. The hottest, most massive stars in such a galaxy, young, brilliant, short-lived objects many times more luminous than our Sun, emit copiously in the ultraviolet, flooding the surrounding interstellar medium with ionizing radiation and driving the powerful stellar winds and supernova explosions that enrich that medium with heavy elements. This ultraviolet light, when it is not absorbed by surrounding gas and dust within the galaxy itself, begins its journey outward into the intergalactic medium, traveling at the speed of light through a universe that is, at this early epoch, far denser and more turbulent than the one we inhabit today. Dangerous as that light travels, the universe continues to expand around it, and the expansion stretches the wavelengths of the light in proportion to the factor by which the universe has grown since the light was emitted. A photon that began its journey as ultraviolet light, with a wavelength of perhaps JWST nanometers, arrives at the Webb telescope with a wavelength that has been stretched by a factor of roughly 13, corresponding to the ratio of the universe's current size to its size at the moment of emission, and so it arrives as infrared light with a wavelength of nearly 2 micrometers. This is squarely within the sensitivity range of Webb's near-infrared camera, known as NIRCam, which can detect light at wavelengths between Lingdent-Los and U micrometers with a sensitivity that surpasses any previous space-based infrared instrument by factors that, in some observing modes, reach into the hundreds. When a photon from a galaxy at redshift 12 finally strikes one of the detector pixels of NIRCam after a journey of more than 13 billion years, it is an event of almost philosophical weight, a piece of information that has been in transit since before the Earth existed, now finally being read by a civilization that built an instrument capable of receiving it. The telescope's ability to take spectra of these distant galaxies, to spread their light out by wavelength and read the pattern of emission and absorption lines that encode information about their composition, temperature, density, and kinematics, adds another dimension of richness to the observations. Spectroscopy is, in a very real sense, the Rosetta Stone of astrophysics. It is the technique through which we learned that the Sun and stars are made of the same elements as the Earth, that galaxies are moving away from us at speeds proportional to their distances, that the universe is expanding, and that the intergalactic medium is permeated by clouds of hydrogen and helium that absorb the light of background quasars in distinctive patterns known as the Lyman alpha forest. For the study of early galaxies, spectroscopy provides the precise redshift measurements that transform a suggestive photometric detection into a confirmed observation. Spectroscopy detection and it provides the line ratios and continuum shapes that allow astronomers to determine whether a galaxy's light is dominated by star formation, by an active galactic nucleus, or by some combination of the two, a distinction that matters enormously for interpreting the galaxy's mass, luminosity, and evolution. Den NIRSpec, the near-infrared spectrograph aboard the Webb telescope, has a remarkable capability called multi-object spectroscopy. Implemented through a device called a microshutter assembly, a grid of roughly wuzzers ling individually addressable tiny shutters, each about by micrometers in size, that can be opened or closed in arbitrary patterns to allow light from many different objects in the telescope's field of view to enter the spectrograph simultaneously. This means that in a single observation, NIRSpec can obtain spectra of hundreds of galaxies at once, dramatically accelerating the process of spectroscopic confirmation that transforms candidate detections into established science. The efficiency this enables is not merely a technical convenience. It is a scientific revolution in the making, allowing surveys that would have taken decades with previous instruments to be completed in months, and opening up statistical studies of galaxy populations in the early universe that were simply not possible before. The results emerging from these spectroscopic surveys are already reshaping our picture of the early universe in ways that go beyond the question of galaxy masses alone. They are revealing, for instance, that the intergalactic medium at redshifts above 6, during and just after the period known as the epoch of reionization, when the first galaxies and quasars ionized the neutral hydrogen that had filled the dot, universe since recombination was more complex and more spatially variable than simple models predicted. Reionization was not a uniform, simultaneous event that swept through the universe like a wave at a single cosmic moment. It was a patchy, inhomogeneous process driven by the first sources of ionizing radiation, galaxies, quasars, and perhaps other objects we have not yet fully identified, each carving out a bubble of ionized gas around dot itself that gradually expanded and merged with the bubbles of neighboring sources until the entire intergalactic medium was ionized. The precise timing, topology, and sources of reionization are questions that the Webb telescope is beginning to answer with new clarity, and the answers have implications for our understanding of the very galaxies, whose existence is surprising us, because the properties of the early galaxies, their escape fractions of ionizing radiation, their star formation rates, their clustering, are intimately connected to how and when reionization proceeded. There is Leishal's, there is a particular galaxy, or rather, a class of galaxies that has emerged from the Webb observations as a kind of emblem of all these intertwined puzzles, and it is worth dwelling on its characteristics with some care. These are galaxies sometimes referred to in the literature as little red dots, a whimsical but descriptive nickname for compact, red-colored objects detected in deep Webb imaging surveys that appear at first inspection to be straightforward high-redshift galaxies, but turn out, upon spectroscopic examination, to be something considerably more ambiguous and considerably more interesting. The name refers to their appearance in Webb's imaging data, small, unresolved or barely resolved sources with colors that are red in the infrared, suggesting either the presence of significant dust attenuation or old stellar populations with red spectral energy distributions, or the contribution of a dust-reddened active galactic nucleus, or some combination of all three. When NER-spec spectra are obtained for these objects, some of them show the broad emission lines characteristic of gas moving at thousands of kilometers per second around a central massive object, a signature of an active galactic nucleus, while simultaneously showing the narrower emission lines associated with star formation in the surrounding galaxy. The coexistence of these two signals, in objects that are compact and very luminous and exist at redshifts that place them within the first billion years of cosmic history, raises a set of questions that current theoretical models can address only partially and tentatively. Then, are these little red dots primarily galaxies in a brief, intense phase of star formation, their red colors caused by the dust produced by that very star formation? Are they primarily active galactic nuclei, accreting supermassive black holes, whose light dominates the spectral energy distribution and makes the host galaxy appear more massive and more luminous than it would be on its own? Are they something genuinely new, a class of object for which we do not yet have an adequate theoretical framework? The honest answer at this relatively early stage of the Webb era is that we do not yet know with certainty, and that the uncertainty itself is productive, driving new observations, new models, and new conversations between observers and theorists that are among the most stimulating in contemporary astrophysics. What is clear is that these objects are real. Their redshifts are confirmed spectroscopically. In many cases, their luminosities are extraordinary, their compactness is measured, their emission line properties are documented, and that they represent a population of objects in the early universe that demands explanation. The question of active galactic nuclei in the early universe is, in itself, a story of considerable depth and complexity that weaves through the broader narrative of early galaxy formation in ways that are difficult to fully disentangle. at the center of virtually every massive galaxy in the present-day universe, including our own Milky Way, whose central black hole, known as Sagittarius Apista, has a mass of approximately 4 million solar masses. There sits a supermassive black hole. In most galaxies today, including our own, these black holes are relatively quiescent, accreting only small amounts of matter and producing little luminosity compared to the galaxy's stellar output. But in the early universe, the black holes at the centers of at least some galaxies were accreting voraciously, converting infalling matter into radiation with an efficiency that can, in principle, reach 10% of the rest mass energy of the accreted material, a far higher efficiency than nuclear fusion, which converts only about T% of hydrogen mass into energy. These accreting black holes, when their luminosity is high enough, are visible across the universe as quasars, and the most distant quasars known, several of which have now been detected at redshifts above 7, with one confirmed at a redshift of C, corresponding to a time when the universe was only about Lubititious million years old, already host black holes with masses of hundreds of millions to billions of solar masses. How these black holes grew so large, so quickly, is itself a major unsolved problem, one that parallels and intersects with the puzzle of early massive galaxies in ways that suggest both phenomena may share a common root in the physics of the very early universe, a common root that may lie in the particular conditions of the universe's first few 100 million years. When the density of matter was higher, the temperatures of gas clouds were shaped by a radiation field, quite different from the one that pervades the universe today, and the absence of heavy elements meant that the cooling and collapse of gas proceeded along pathways that have no precise analog in the more chemically enriched environments of later cosmic epochs. To understand those conditions, and to understand why they might have produced both the massive galaxies and the massive black holes that the Webb telescope is revealing, it is necessary to travel back, conceptually, imaginatively, and mathematically, to the very beginning of the story, to the first moments after the Big Bang, when the universe was a place of extraordinary simplicity and extraordinary violence, and to trace the chain of physical events that connected that primordial simplicity to the complex, structured, astonishing cosmos that the telescope is now mapping with such patient precision. The universe, in its first fraction of a second, was a plasma of extraordinary density and temperature, a state so extreme that the fundamental particles of matter, quarks and leptons, existed freely rather than bound into the protons and neutrons that would later constitute the nuclei of atoms. As the universe expanded and cooled, quarks combined into protons and neutrons during a period called the QCD phase transition, and within the first few minutes, nuclear fusion reactions bound some of those protons and neutrons together into the nuclei of helium, deuterium, and trace amounts of lithium, a process called Big Bang nucleosynthesis, whose predictions match the observed abundances of these light elements with remarkable precision, providing one of the foundational confirmations of the hot Big Bang model. For the next several 100,000 years, the universe remained opaque, a dense fog of charged particles and photons so tightly coupled that light could not travel freely, until, as in the Forschul's Sembai-Bashers Ling years, at an age of approximately Sembai-Bashers Ling years, the temperature dropped enough for protons and electrons to combine into neutral hydrogen atoms. This event, called recombination, allowed photons to stream freely for the first time, producing the cosmic microwave background radiation that we detect today as a nearly uniform glow of microwave light coming from every direction in the sky, with tiny temperature fluctuations of about 1 part in 100,000 that encode the seeds of all subsequent cosmic structure. Yet, those tiny fluctuations, slight overdensities and underdensities in the distribution of matter at the time of recombination were the raw material from which everything that followed was constructed. Under the influence of gravity, the overdense regions attracted more matter, growing denser still, while the underdense regions became increasingly empty. The dark matter, which did not interact with light and therefore was not subject to the radiation pressure that kept ordinary matter smooth until recombination, had already begun this process of gravitational collapse earlier, forming the scaffolding of dark matter halos into which ordinary matter subsequently fell. The first dark matter halos to collapse were the smallest ones, with masses of perhaps 1 million solar masses, tiny by galactic standards, and they formed within the first few 100 million years. Within these halos, gas fell inward, compressed, and began to cool, primarily through the radiation of molecular hydrogen, which, in the absence of any heavier elements, was the principal coolant available. As the gas cooled and densified, it eventually reached the conditions necessary for gravitational instability and fragmentation into individual protostars, the first stars in the universe, the population 3 stars, beginning to ignite their nuclear fires in the darkness of a cosmos that had, until that moment, been without any source of light other than the fading glow of the cosmic microwave background. These first stars were, by all theoretical accounts, extraordinary objects, massive, luminous, and hot in ways that stars formed today, in metal-enriched molecular clouds, are not. The absence of heavy elements in the primordial gas meant that the cooling mechanisms available to collapsing gas clouds were limited, preventing the fragmentation into small clumps that characterizes star formation in the present-day universe, and instead allowing the formation of very massive objects, perhaps hundreds of times the mass of the Sun, burning at temperatures far exceeding those of typical modern stars and emitting prodigious quantities of ionizing ultraviolet radiation. These population 3 stars lived brief, violent lives, a few million years at most for the most massive among them, before dying in catastrophic supernova explosions or, for the very most massive, collapsing directly into black holes without a conventional supernova. Both outcomes had profound consequences for the subsequent evolution of the universe. The supernova explosions enriched the surrounding gas with the first heavy elements, carbon, oxygen, silicon, pp, iron, changing the cooling properties of that gas and paving the way for the formation of a second generation of stars, the population 2 stars, which formed from this slightly enriched material and whose properties, while still quite different from present-day stars, were closer to what we observe in the oldest stars of the Milky Way today. The black hole remnants of the most massive population 3 stars, meanwhile, may have provided the seeds around which the supermassive black holes of later galaxies grew. A hypothesis that is intellectually appealing, but that faces the significant challenge of explaining how a black hole of perhaps a few hundred solar masses could grow to billions of solar masses within only a few 100 million years, a growth rate that seems to require either sustained near-Eddington accretion, accretion at the theoretical maximum rate, or a series of mergers, or both. It is within this context, this complex, rapidly evolving early universe of first stars, first black holes, first small galaxies, and an intergalactic medium in the process of being reionized, that the massive early galaxies revealed by the Webb telescope must be understood. They did not appear from nowhere. They are the products of physical processes that began in the first fraction of a p pre-T second after the Big Bang and unfolded over the subsequent hundreds of millions of years, and the question of why they are more massive than expected is ultimately a question about which of those processes operated differently than our current models assume, and why. The answers, when they come, and they will come gradually, through the accumulation of observations and the refinement of theory in the manner that science has always advanced, will tell us something fundamental not just about galaxies, but about the nature of dark matter, the physics of star formation in extreme environments, the growth of supermassive black holes, and possibly about aspects of cosmology that extend beyond the standard model in ways we cannot yet fully anticipate. One of the most intriguing theoretical proposals that has gained traction in the context of the Webb observations concerns the possibility that star formation in the early universe was significantly more efficient than in later epochs, that the fraction of available gas that was converted into stars per unit time, per unit of halo mass, was substantially higher in the first billion years than at any later time. In the standard picture, star formation efficiency is regulated by feedback processes, the energy and momentum injected into the surrounding gas by newly formed stars through radiation pressure, stellar winds, and supernova explosions, which can heat and expel gas from star-forming regions and thereby limit the rate at which new stars form. This self-regulation is an important feature of the standard model, and it is necessary to explain why the observed star formation rates in galaxies across cosmic time match the predictions reasonably well. But some theorists have argued that in the very early universe, the conditions were such that this self-regulation was less effective, that the gas in early galaxies was so dense and so rapidly infalling that stellar feedback could not keep pace with it, allowing star formation to proceed at a higher efficiency than models calibrated on later epoch observations would predict. If this is correct, it would mean that early galaxies could accumulate stellar mass faster than the standard model assumes, potentially explaining the apparent excess of massive objects at high redshift without requiring any modification of the underlying cosmological framework. A related but distinct possibility concerns the role of what are sometimes called direct collapse black holes, a proposed pathway for the formation of supermassive black hole seeds that bypasses the population 3 star route entirely. In regions of the early universe where the radiation field was intense enough to dissociate molecular hydrogen, the primary coolant that would otherwise allow gas to fragment into small stars, a massive gas cloud, could potentially collapse directly into a black hole of perhaps 100,000 to 1,000,000 solar masses without first passing through a stellar phase. This would provide a much more massive starting point for the subsequent growth of a supermassive black hole, making it far easier to reach the billion solar mass scales observed in the most distant quasars within the available time. Direct collapse black holes remain theoretical objects. No confirmed example has yet been identified observationally, but the Webb telescope is actively searching for their signatures, and several candidate objects have been their identification resting on the specific pattern of emission lines and continuum shapes that such objects would be expected to produce. The confirmation of even a single direct collapse black hole would be a landmark discovery, providing a crucial piece of the puzzle of how the universe, supermassive black holes came to be so massive so quickly. Alongside these theoretical experiments, there is an observational program of extraordinary ambition and scope unfolding through the Webb telescope's various science programs. Both the guaranteed time observations that were awarded to the scientists most closely involved in the telescope's development and the general observer programs that have been selected through competitive peer review from proposals submitted by the broader astronomical community. Among the most important of these programs for the study of early galaxies are the deep field surveys, observations of small patches of sky conducted over many hours or even many tens of hours of telescope time. building up the signal-to-noise ratio necessary to detect the faintest and most distant objects accessible to the instrument. The Webb telescope has already produced several such deep fields, including observations of the area around the original Hubble Deep Field and its successors, allowing direct comparison between what Hubble saw and what Webb reveals in the same regions of sky, a comparison that is itself scientifically illuminating, demonstrating concretely what the new telescope's enhanced sensitivity and infrared capability add to our knowledge of the distant universe. In these deep fields, galaxies are visible at redshifts that were simply inaccessible to Hubble, and the properties of those galaxies, their morphologies, their colors, their clustering, their sizes, are already beginning to constrain theoretical models in ways that will take years to fully digest and understand. And that process of digestion, of careful, methodical comparison between observation and theory, between what the data says and what the models predict, is itself one of the most genuinely human aspects of science. Slow, collaborative, argumentative in the best sense, full of false starts and unexpected connections and moments of sudden clarity that arrives sometimes in the middle of a seminar, sometimes in the quiet hours before dawn when a researcher is staring at a spectrum on a computer screen and something in the pattern of lines suddenly resolves into meaning. It is a process that cannot be rushed, and the Webb telescope, for all the speed with which it is accumulating data, is feeding into a scientific enterprise that will take decades to fully absorb and interpret what it is seeing. We are, in a very real sense, still in the early pages of a story whose full arc we cannot yet perceive, and there is something genuinely exciting about that, about living at a moment when the instruments have outrun the theory, when the observations are ahead of the explanations, when the universe is, in a manner of speaking, telling us things we did not know to ask. Among the most important and most carefully studied of the early Webb results bearing on the question of massive early galaxies is a set of observations conducted as part of the SEERS program, the Cosmic Evolution Early Release Science Survey, which used Webb's NERCam instrument to image a region of sky previously observed extensively by Hubble, allowing the kind of direct comparison that reveals most clearly what the new telescope adds. SEERS, led by Stephen Finkelstein of the University of Texas at Austin, and involving a large international collaboration of researchers, was one of the first programs to produce deep Webb imaging data available to the community, and it generated an immediate flood of scientific papers examining the galaxy population it revealed. Among the objects identified in SEERS data was a galaxy designated Maisie's Galaxy, named after Finkelstein's daughter, which appeared in the initial photometric analysis to be at a redshift of approximately 12, making it one of the most distant galaxy candidates identified at the time of its discovery. Subsequent spectroscopic observations confirmed a redshift of C, placing this galaxy at a look-back time of approximately C billion years, a time when the universe was only about million years old. The existence of a galaxy luminous enough to be detected in imaging data of this depth at such a redshift is itself a statement about the rate of early galaxy formation, and Maisie's Galaxy is now one of a growing catalogue of spectroscopically confirmed galaxies at redshifts above 10 that the Webb telescope is assembling with increasing efficiency as its observing programs accumulate. But perhaps even more striking than the individual high redshift galaxies confirmed by the Webb telescope are the statistical properties of the galaxy population as a whole, the luminosity function, which describes how many galaxies of each luminosity exist per unit volume of space at a given redshift, and the stellar mass function, which provides the equivalent description in terms of stellar mass rather than luminosity. These statistical descriptions are among the most powerful tools available to observational cosmologists because they can be directly compared to the predictions of theoretical models and simulations, providing a quantitative test of whether those models correctly capture the physics of galaxy formation. In the era before Webb, measurements of the galaxy luminosity function at redshifts above 6 were already suggesting some tension with model predictions at the bright end, an excess of luminous galaxies relative to what the models expected, but the uncertainties were large enough that the tension was not universally regarded as definitive. Webb's deeper, more sensitive, and more complete surveys have sharpened these measurements considerably, and the tension at the bright end of the luminosity function at high redshifts has, if anything, become more pronounced rather than less as the data have improved. The physical interpretation of this bright end excess is a matter of active debate, and it connects directly to the questions about star formation efficiency, feedback, and dust attenuation that have already been introduced. One important possibility is that the bright end excess is not primarily a reflection of more stellar mass than expected, but rather of less dust attenuation than expected. Dust, the tiny solid particles of carbon, silicon, and other materials produced by dying stars and distributed through the interstellar medium, absorbs and scatters starlight, preferentially affecting shorter wavelengths and causing galaxies to appear redder and dimmer than they would in its absence. The degree to which dust attenuates the light of a galaxy depends on the geometry of the dust distribution, the total dust mass, and the grain size distribution, and all of these quantities are expected to evolve with cosmic time because dust is produced by stars and its abundance therefore reflects the cumulative star formation history of the galaxy. In the very early universe, galaxies may have had less time to accumulate dust, meaning that their starlight escaped more freely and they appeared more luminous per unit stellar mass than galaxies at later epochs. If this is the case, then the bright end excess seen by Webb would not necessarily imply more stellar mass than expected. It might simply reflect the lower dust content of early galaxies, which would make them brighter for their mass and therefore more easily detectable. Distinguishing between these possibilities requires observations at multiple wavelengths, including the mid-infrared wavelengths accessible to Webb's MIRI instrument, which can probe the thermal emission from warm dust and thereby constrain the dust content of early galaxies in ways that purely optical or near-infrared observations cannot. MIRI, the mid-infrared instrument, is in many ways the most technically challenging of Webb's 4 science instruments, operating at wavelengths between 5 and 28 micrometers and requiring cooling to approximately Kelvin, just 7 degrees above absolute zero, achieved through a dedicated cryocooler system. At these wavelengths, MIRI can detect the thermal emission from dust in galaxies across a wide range of redshifts, the mid-infrared spectral features of polycyclic aromatic hydrocarbons that are traces of star formation activity, and the broad emission lines of active galactic nuclei that fall into the mid-infrared at high redshifts. For the study of the most distant galaxies, MIRI's sensitivity is limited by its longer wavelengths and smaller diffraction-limited resolution relative to the near-infrared instruments. But for galaxies at moderate to high redshifts, say redshifts of 2 to 6, corresponding to the period of peak cosmic star formation activity known as cosmic noon, MIRI is extraordinarily powerful, providing constraints on galaxy properties that complement and extend what can be learned from NERCam and NERSpec alone. The combination of all 4 of Webb's instruments, used together in coordinated observing programs, provides a multi-wavelength portrait of early galaxies that is genuinely unprecedented in its completeness and its depth. One of the most profound aspects of what the Webb telescope is revealing about early galaxies is not merely their existence or their masses, but their morphologies, their shapes, their internal structures, the spatial distribution of their stars and gas as revealed by the telescope's extraordinary angular resolution. In the visible light images produced by the Hubble Space Telescope, galaxies at redshifts above 2 or 3 typically appeared as small, irregular, often clumpy blobs, objects that seemed to bear little resemblance to the grand, spiral, and elliptical galaxies of the nearby universe, suggesting that the familiar morphological categories of present-day galaxies had not yet been established at early times, and that high redshift galaxies were genuinely more disordered and more turbulent than their modern counterparts. The Webb telescope, observing the same galaxies in the infrared, which corresponds to rest frame optical dot, or even rest frame near-infrared light for the most distant objects, tracing the distribution of older, more evolved stellar populations rather than the young, hot stars that dominate in the ultraviolet, is revealing a significantly different picture. Many galaxies that appeared irregular and clumpy in Hubble images show, in Webb images, clear evidence of ordered structure, disks, bars, bulges, even hints of spiral arms, at redshifts that place them within the first few billion years of cosmic history. This discovery that disk galaxies and other ordered morphological structures were already in place, much earlier than expected, is itself a significant challenge to standard models of galaxy formation, which predict that the early universe should have been a place of frequent mergers and violent interactions that would disrupt ordered structure and maintain the irregular, turbulent morphologies seen in Hubble observations. The presence of well-ordered disks at high redshifts implies either that disk formation is more rapid and more robust than models suggest, or that the merger rates in the early universe were lower than predicted, or that disks can form and reform quickly after merging events, or some combination of all these factors. Understanding galaxy morphological evolution, the processes by which galaxies acquire, lose, and regain ordered structure over cosmic time, is one of the central problems of extragalactic astronomy, and the Webb telescope is providing observational constraints on this problem at epochs that were previously inaccessible, with a clarity and resolution that is forcing theorists to revisit their models with new urgency. The internal kinematics of early galaxies, the patterns of motion of their stars and gas, measurable through spectroscopy, add yet another layer of information to this morphological picture. A galaxy whose gas is moving in ordered rotation around a common center, with a velocity field that follows the pattern expected for a disk supported by centrifugal force against gravitational collapse, is a galaxy that has achieved a degree of dynamical maturity that takes time to develop, and that is associated with a relatively quiescent merger history. Conversely, a galaxy whose kinematic structure is irregular and turbulent, with large random motion superimposed on any rotational component, is one that is either in the process of a merger, or has recently experienced one, or is accreting gas from the surrounding intergalactic medium in a chaotic fashion. Webb's InERSpec instrument, with its multi-object spectroscopy capability and its ability to take integral field spectroscopy, obtaining a spectrum at every spatial position within a small area of the sky, is beginning to map the kinematic structure of early galaxies in ways that were previously possible only for much nearer objects, and the results are adding important nuance to the picture of early galaxy evolution that the imaging data alone cannot provide. Some early galaxies show surprisingly ordered rotation, others show the turbulent, dispersion-dominated kinematics expected for young, rapidly evolving systems, and the distribution between these two categories, and its dependence on galaxy mass, redshift, and environment is a subject of intense ongoing investigation, an investigation that is unfolding in real time across dozens of research groups on multiple continents, with new results appearing on the RxIV preprint server at a pace that sometimes makes it difficult, even for specialists to keep up with the full scope of what is being discovered. There is something almost vertiginous about the current moment in observational cosmology, a sense of standing at the edge of a great expansion of knowledge, watching the map of the early universe fill in with new detail at a speed that has no real precedent in the history of the field. The Webb telescope is not merely confirming or refining what we already knew. It is opening doors into regions of cosmic history that were previously sealed. And what lies behind those doors is turning out to be richer, stranger, and more challenging to understand than almost anyone anticipated. Billions to appreciate the full significance of what is being found, it helps to step back from the individual observations and consider what the early universe looked like as a whole, not as a collection of isolated objects, but as a connected, evolving system in which galaxies, gas, dark matter, and radiation were all interacting with each other across vast scales in ways that determine the properties of every individual galaxy we observe. The large-scale structure of the universe, the web of filaments, sheets, nodes, and voids that constitutes the cosmic web, was already beginning to take shape in the first billion years. Its architecture determined by the same initial density fluctuations that produced the temperature anisotropies in the cosmic microwave background. Dark matter, responding to gravity and to its own internal dynamics, collapsed along these fluctuations into a network of filaments and nodes, with the densest nodes becoming the sites of the most massive dark matter halos and, subsequently, the sites of the most massive galaxies. Flowed along the filaments, channeled by the dark matter scaffolding into the halos where it could cool and form stars, and the first galaxies formed preferentially at the intersections of filaments, the nodes of the cosmic web, where the gas density was highest and the conditions for star formation most favorable. Reads, this picture of galaxy formation within the cosmic web has important implications for understanding why some early galaxies are so massive. If the most massive early galaxies formed at the densest nodes of the cosmic web, they had access to a larger reservoir of gas than galaxies forming in less dense environments, and they may have been fed by multiple filaments simultaneously, providing a continuous supply of cold gas that could sustain high star formation rates over extended periods. The theory of cold streams, narrow filaments of cold, dense gas penetrating through the hot gas that fills massive dark matter halos and delivering fuel directly to the central galaxy without being shock heated to the virial temperature of the halo, has been developed by Avishai Deckel and colleagues as a potential explanation for the high star formation rates of massive high redshift galaxies, and it remains one of the most influential theoretical frameworks for understanding galaxy formation at early times. In this picture, the massive early galaxies revealed by Webb are not anomalies requiring exotic physics to explain. They are the expected products of the densest, most well-connected nodes of the early cosmic web, fed by cold streams of gas that bypassed the usual heating processes and delivered material directly to the star-forming regions of the galaxy at rates far exceeding what the standard feedback-regulated picture would predict for isolated halos of similar mass. The cold stream picture has been supported by a number of theoretical simulations, and it makes specific predictions about the geometry and kinematics of gas accretion in high redshift galaxies that the Webb telescope, with its combination of imaging and spectroscopic capabilities, is beginning to test observationally. The detection of Lyman alpha emission, the characteristic emission line of neutral hydrogen at a rest frame wavelength of E-byte Arces-Edian low nanometers, redshifted into the optical or near-infrared for high redshift galaxies, in extended halos around early galaxies, a phenomenon known as Lyman alpha nebulae, or blobs, has been interpreted in some cases as evidence for cold gas accretion along filaments, and Webb's sensitivity to Lyman alpha at high redshifts, combined with its spatial resolution, is providing new constraints on the extent and morphology of these nebulae. Understanding the geometry of gas accretion, how gas reaches the central galaxy, at what rate, in what physical state, is essential for understanding why some early galaxies grew so rapidly, and the Webb telescope is beginning to provide the observational leverage needed to distinguish between competing theoretical pictures. But the cosmic web is not merely a passive structure that channels gas to galaxies. It is also the medium through which the effects of galaxy formation propagate across large scales, carried by the winds of gas driven outward by supernova explosions and active galactic nuclei, by the ionizing radiation that escapes from galaxies and reionizes the intergalactic medium, and by the mechanical energy deposited by radio jets launched by the most powerful accreting black holes. These feedback processes, collectively referred to as galaxy feedback, and representing one of the most active areas of both observational and theoretical research in contemporary astrophysics, shape not only the galaxies from which they originate but the surrounding intergalactic medium and, through it, neighboring galaxies and their ability to accrete gas and form stars. The large-scale effects of galaxy feedback are among the most difficult things to capture in theoretical models and simulations, because they involve physical processes operating on scales ranging from the subparsec scales of the accretion disk around a black hole to the megaparsec scales of the intergalactic medium, a dynamic range of more than 20 orders of magnitude that no simulation can yet fully resolve. Instead, the effects of feedback on small scales must be approximated through what are called subgrid prescriptions, parametrized recipes, that capture the gross effects of feedback without resolving its detailed physics, and the results of simulations are sensitive to the specific choices made in implementing these prescriptions in ways that introduce significant theoretical uncertainty.